Now we're back and let's delve into some more details of reconnection. Specifically, start thinking about something called the reconnection rate. Okay, in other words, the rate at which magnetic field, magnetic flux in particular, is annihilated, because as we said, as we pointed out, the whole point of reconnection conceptually, yes, it's cutting and pasting field lines, which is not permitted in MHD, and so you have to invoke fancy non-ideal effects such as finite resistivity and everything. Where the finite resistivity comes from, that's another matter, but we will see. But the bottom line is, the reason reconnection is so interesting to astrophysicists is that it's a potential way of converting magnetic energy into heat. Also, bulk kinetic energy of the flow. And so essentially the amount of magnetic energy that's converted is essentially, it depends upon the amount of magnetic flux that's annihilated, that's eaten up. Right? And so the rate at which this magnetic flux is annihilated is very important. This is called the reconnection rate, or it's related to what's called the reconnection rate. And let's embark on a little bit of discussion of this topic. Right? So this is what's called the Sweet-Parker scenario, after the two scientists, Eugene Parker and Sweet, who almost independently came up with this particular kind of calculation, and it's all explained in this figure here. The basic details are the same as what we've seen earlier. So you've got two anti-parallel field lines. You see one going this way and the other going this way, right? Two anti-parallel field lines which are being brought close to each other at a velocity vi, okay, at a speed v sub I, right? As they come close to each other, the straight field lines get a little curve like this, right? And finally what happens is, this field line reconnects with this field line to give a thing like this, and this one reconnects with this one to give a configuration that looks like this. And right here, this is the reconnection region, or whatever, the reconnection, variously called the reconnection region, or often called the X point, for obvious reasons. You see, the magnetic field configuration looks like an X, or null point, so on and so forth. Okay, it's in this small region that all the action happens. Okay, now from Ampere's law, we know simply because you've got oppositely directed fields, a field pointing this way and a field pointing this way. Right here in between, you need to have a current. In this case, a current that's coming out of the plane of the screen. So this dot would be the head of the arrow. Okay, and you can either think in terms of current density, or you can think in terms of electric field. Okay, because from Ohm's law, you just have J is equal to sigma E. Now you have a finite sigma, not an infinite sigma, right? This is the conductivity, and so the J and the E go hand in hand. They are the same essentially, except for a factor of sigma. And yeah, so you remember, I mean, the whole point of ideal MHD was that the sigma was infinite. Therefore, there was no way you could have any electric field in the bulk fluid. In ideal MHD, there is no scope for an electric field. Whereas here, you see, at least in this very local region, you have the appearance of an electric field. So this is yet another way you can understand this oft invoked statement of stated thing that ideal MHD is violated in reconnection. What one really should say is ideal MHD is violated in the reconnection region right here. Okay, via why? Well, via finite resistivity effects, or via the appearance of an electric field like that. In this case, the electric field is pointing out of the plane of the screen, and so this would be the head of the arrow. Okay, right. So let us now, by way of dimensions, let us think of the thickness of this current sheet as 2 times small l. Okay, so the current sheet thickness is 2 times small l, whereas the macroscopic dimensions are 2 times large L. Why the 2? Well, you cut it in between, and so this would be large L, this would be large L, and even here you cut it like this, and so on one side you will have small l, the other side you would have small l. The other thing this tells you is that this figure attempts to show to you is that you have these field lines approaching very close together, they come very close together, and then finally post reconnection what happens is they snap like this. This is the after kind of field line, like this one and this one. Okay, the field lines snap apart and they move out at a velocity v naught. So initially this would be the velocity at which the field lines are being brought together, and this v naught would be the velocity at which the field lines are snapping apart. Okay, so having done this, now let us see, like we said, mass is conserved but magnetic flux is not. That's the whole point. Magnetic flux not being conserved is yet another way you can understand the violation of ideal MHD. In ideal MHD, magnetic flux is always conserved, right. So in this case, at least in the reconnection region, magnetic field is not conserved, magnetic fields are annihilated. Okay, so let us, presumably due to resistive effect. Okay, so right, and by the way, we are talking about a steady state scenario in which there is no, in other words, everything appears steady. In other words, the rate at which mass is swept in is equal to the rate at which mass is leaving. So in steady state, the rate at which magnetic flux is swept in is equal to the rate at which is annihilated. There is a whole definition of steady state. Okay, there is no difference in these rates, otherwise this would be violated. Okay, so this is another way you define the steady state. You're sweeping in magnetic flux at a certain rate into the reconnection region, okay, and it's being eaten up. Okay, the magnetic flux is being destroyed or annihilated at a certain rate, and these two rates are equal. Okay, that is another definition of steady state. Okay, so what is the rate at which magnetic flux is swept in? You see, Vi is the speed at which the magnetic flux is brought in. Okay, and this whole annihilation is happening over the thickness of the current sheet. You agree, 2L, and therefore the rate would be Vi over L, like that. In other words, the dimensions of Vi over L would be per second. You agree with that? So this gives you Gauss per second. Okay. Okay. Now, so this is the rate at which magnetic flux is swept in, this thing. Now, what is the rate at which is annihilated? Now, annihilation follows from finite resistivity effects. So now what happens is you have the induction equation, which now looks like this: dB dt equals lambda, where lambda includes all the resistive terms, del square B. Okay, generally you would have seen the induction equation as this. Curl of right, and that is all, because the other resistive term was generally not important. this term is generally not important. In this case, the opposite is true. This is not important. Okay. And so, it is only this term which is important. So, you have dB dt equals lambda, del square b, and from order of magnitude analysis, you see the dB dt is like a Gauss per second, and the Gauss per second is what? So, you have a lambda, let us keep lambda as it is, okay, and this del square b is something like right 1 over L square, because it is like a d over dx kind of thing, d over dx, d over dy. And where is why are we writing this as 1 over small l squared? Because the whole point is that d over dx tells you the rate of change of magnetic field in space. Where is the magnetic field changing? The magnetic field is changing only in this region, isn't it? It is really, or rather is changing over this length scale. So, it is correct to replace the d over dx by something like 1 over L, and therefore, d square over dx square is something like 1 over L square, where L is a small l, the dimensions of the reconnection region, because that is where the d over dx is appreciable. Outside of that, there is really no change. D over dx is as good as 0. That is why we write the magnetic fields are annihilated as lambda we keep it as it is times b naught over L squared. The L squared comes from the del square b, and if you look at the dimensions of lambda, if you look at the dimensions of L, this works out to be b naught b per second, and it has to. The left hand side is b per second, so it works out. Now, what you do, the whole point of the steady state assumption is that you equate the rate at which magnetic flux is swept in to the rate at which magnetic flux is annihilated. So, these two quantities need to be equated. So, you equate this to this, okay. You write Vi b naught over L equals lambda b naught over L squared, okay. This gives us the all important width of the reconnection region. Very, very important. How thick is the reconnection region? From this, I strike off b naught and I strike off one factor of L, right. I strike off this and I get L equals lambda over Vi. In other words, lambda is directly proportional to the resistivity. Okay. So, the more resistive, okay, the larger the value of resistivity in this region, the thicker the dimensions of the region where all this reconnection action is happening. Okay. The more the resistivity, the thicker this region. The less the resistivity, the thinner this region. Okay. Maybe I should use the word anomalous resistivity, because in the bulk of the flow, the resistivity is technically 0. Okay, it is only in here that some magic resistivity, due to some non-ideal effects, resistivity is starting to appear. It is kind of an anomalous effect. So, it is really an anomalous resistivity we are talking about here. Okay. So, the larger that anomalous resistivity, the thicker the dimensions of the of the reconnection region. Also, smaller the inflow velocity, right, the thicker the dimensions of the reconnection region. That is what this formula is telling us. Okay. Yeah. So, that is about the the width of the reconnection region, this quantity, very important. Okay. But we also need to consider the macroscopic length, the larger dimension. What about this capital L? As you guessed, we derived this small l from a conservation or non-conservation of magnetic flux. Okay. So, the capital L will be derived from conservation of mass. Okay. Assuming, so how about its length? In other words, how about its length, capital L? This is what we are talking about. What is capital L? So, in order to do that, we use mass conservation, and assuming incompressibility, let's neglect compressibility effects for a minute, just to make life simple. Otherwise that introduces yet another, that throws a spanner in the works, as it were, and it introduces yet another complication. So let's not bother ourselves with that complication. So let us say, and we know the incompressible condition is given by this divergence of V equals 0. And so if divergence of V equals 0 is equivalently expressed as Vi times large L is equal to V naught times small l, where Vi is the inflow velocity, or shall we say, to keep it simple, inflow speed, and this is the outflow speed. And what outflow are we talking about? Well, this outflow right here. This is what we are talking about, and this would be the inflow. Okay, right. So Vi times this is essentially the the one-dimensional equivalent of divergence of V equals 0. Okay, so now the ratio of the large L to the small l is given by the ratio of V naught to Vi. Okay, that's what this is telling us. Now, total pressure, now there has to be pressure equilibrium across the current sheet. Okay, otherwise the current sheet will either keep expanding or it will keep collapsing if there is no pressure equilibrium. It's only if there is pressure equilibrium that you will have a steady state scenario. Okay, so across the current sheet, so you have P naught, which is kind of inside the current sheet, or inside the reconnection region, right, and this whole thing is outside. So the pressure inside the reconnection region and the pressure outside are balanced. Of course, there are different contributions to the pressure. Outside the reconnection region, you have the gas pressure, which is Pi, and the magnetic field pressure, which is in this case we are writing it in SI units. So instead of B square over 8 pi, you have B square over 2 mu naught. Okay, it's just a change of units. As such, physically nothing different is happening, it's just the way we're writing it. Anyhow, there's gas pressure and magnetic field pressure. Whereas inside the reconnection region, you notice there is no magnetic field pressure, there is only gas pressure. Very curious, isn't it? Why is that? Well, remember, we were saying that inside the reconnection region, the magnetic field is annihilated. The magnetic field is essentially driven down to 0. It's eaten up. Magnetic flux is eaten up. There is no magnetic field right there in that very small reconnection region. That's why you don't have any appearance of a B naught squared. Okay, there is no B naught. Okay, it's a null point. It's an X null, as in null of magnetic field. So there is no magnetic pressure. There's only particle pressure. So inside the reconnection region, there's only particle or gas pressure, and outside you have gas pressure plus magnetic field pressure. So these have to be in equilibrium. Yeah, at the point where the pressure equals P naught, the magnetic field is 0. This is what we just said. Now, integrating the momentum equation, you get the difference in pressures is simply 1/2 rho V naught squared. This is, we neglect the Lorentz forces. Why? Because B is nearly 0 in the reconnection region. So Lorentz forces are J cross B, so it's not so important. So therefore, this gives you something about this is the outflow velocity. This tells you how fast the outflow velocity will be. It depends upon the difference in gas pressures in the reconnection region and outside. Of course, on the mass density, no doubt. Okay, so now taken together, what will happen is you will find out, if you solve these, you will find out that the outflow velocity is essentially the alphane velocity. The alphane velocity far away from the reconnection region, right? In the reconnection region, the alphane velocity falls to 0 because the magnetic flux is 0, right? Taken together, this is what we come up with, and this is the all important reconnection rate. It's really a speed. Okay. So, what this is what's called the reconnection rate. Okay. It's a self-limiting process really. It's not as if you see this, it's not as if I can, Vi is this velocity, right? It's not as if I can drive these oppositely directed magnetic fields together at any arbitrary speed. No, I cannot. I can only drive it with the speed that's commensurate with the fact that whatever magnetic flux I'm bringing in here needs to be eaten away immediately. Okay, the rates have to balance. The rate of bringing together of magnetic flux has to balance the rate at which they are eaten away. Number one. Number two, the mass fluxes have to be equal. Number three, there has to be pressure equilibrium. Okay, otherwise the current sheet will grow thinner and thinner. If you want the current sheet thickness that stays constant with time, there has to be pressure equilibrium. If I have to satisfy all of these three conditions, okay, I find that there is a very specific number for the speed at which I can bring these oppositely directed magnetic fields together, and that is equal to the alphane speed outside in very far from the reconnection region divided by the magnetic Reynolds number, square root of the magnetic Reynolds number, which is defined by this. Okay, the magnetic Reynolds number is defined by the alphane speed times the macroscopic length divided by lambda. Okay, now if the lambda is technically almost close to 0, the magnetic Reynolds number goes to infinity, and vice versa. If the lambda is large, then the magnetic Reynolds number is small. Okay, so this is the all important reconnection rate, and this is just something, this is just a quirk of the terminology. It's what is normally called the reconnection rate is really a reconnection speed. Okay. Now, why are we so concerned about reconnection rate? You see, this is the steady state reconnection. This is the reconnection rate that we derived in the previous slide. Okay, but now this is another thing to ponder. How does this compare with the diffusion rate? In other words, if I write down the okay, and if I dimensionalize these things, B times some T naught inverse B over some L square. If I plug this in, this will give me the diffusion time scale. This T naught inverse is this T naught is the diffusion time scale. How does this compare with the diffusion rate? It's useful, I urge you to work this out. How does this compare with this T naught? Well, this is actually a rate. In other words, this is a time scale. So if you want to convert it into a speed, you have to invoke a length scale. Maybe you should invoke the macroscopic length scale. Okay, so I urge you to compare it with the diffusion rate. Turns out that the diffusion rate is always very, very small. Okay, the reconnection rate is substantially larger. Okay. But the thing is, in astrophysical and we hinted at this a little earlier, problem here is that the magnetic Reynolds number in astrophysical plasmas is very large. Since the resistivity, you see this is the definition of the Reynolds number. If the resistivity is very small, the Reynolds number is very large, and unfortunately the Reynolds number appears in the denominator here. The dependence is a little weak because there is a square root. Okay, so the dependence is a little weak, but still the Reynolds number appears in the denominator. So if the Reynolds number is large, the reconnection rate is small. This is the thing. Okay, so the reconnection rate is small in comparison to what? Small in comparison to the alphane speed. Okay, So, and I wanna, talk a little bit about this sentence in a minute. So, this is not what the observations mandate. What the observations, for instance, what do you really mean by this sentence? Well, let's back up a little bit. Let us consider a specific phenomenon like a flare on the sun in the solar corona, which is a flare is simply an increase in, if you were plotting the say the X-ray flux as a function of time. Okay. And this can be X-ray flux, this can be ultraviolet flux, this can be flux at any wavelength, okay, as a function of time. A flare is just this. It increases and then it decreases. It need not be symmetric like this. Many times the increase is very abrupt and the dying off is very gradual. Either way, this is a flare. You strike a matchstick, flame flares up, that's a flare. Okay, it's just an increase in the number of photons as a function of time. X-ray photons are plotted on the y-axis and the number of photons increases. This is what a flare is. The question is, what is this time scale? Say, 1/2 of maximum time scale. What is this time scale? And so this is what the observations mandate. But mind you, this has got nothing to do with, as such, it's a very indirect thing to relate this time scale to anything like the reconnection time scale. But the thing is, it's as follows. The line of reasoning is as follows. Well, who was responsible for heating the plasma? We are holding the reconnection process to be responsible for heating the plasma, isn't it? So, if the magnetic flux is annihilated at a certain time scale, the heating also happens at approximately that time scale, because it's the annihilated magnetic flux that leads to heating. If the magnetic flux is annihilated over a certain time scale, the heating also happens at that time scale, and therefore, once the plasma is heated over a certain time scale, it will also radiate. Hot bodies radiate. It radiates, and this is observed radiation plotted on the y-axis. So, since the heating occurs at a certain time scale, and then after the heating is turned off, in other words, after the reconnection stops, the flux has to fall, the plasma has to cool. Of course, there are conductivity effects, okay, to be worried about. It's not as if that the region which is radiating is completely thermally isolated from its surroundings. You have to worry about conductivity. But roughly speaking, once the heating is turned off, the plasma has to cool, and so the observed radiation also falls down. So, it's in that sense that the time scale, the observational time scale, is roughly this, and you compare this with the alpine speed that you expect in the medium, and turns out that the time scale over which this happens is roughly similar to the alpine time scale, or something like, So, whereas if you plug in typically assumed numbers for the Reynolds number, the magnetic Reynolds number in astrophysical plasmas, turns out that the VI, the reconnection rate, is actually very, very small. It's nothing close to the alpine time scale, whereas the observations kind of mandate what's called an alpine time scale. So, there's a problem with this nice scenario, and how to solve this problem? Petschek came up with a very innovative solution to solve this problem, and we will talk about this and when we meet next. So, for the time being, thank you.